So the assumptions for multiple linear regression when we're making inference on the slope are the same as they were for simple linear regression and ANOVA. The errors have to be independent, normally distributed, have equal variance, and have mean zero. The normality assumption, remember, is necessary when making inference. In multiple regression, to check the mean zero, the linearity assumption, and equal variance assumption, you need to check it individually for each predictor and also on the residuals versus predicted plot. So for our regression, using the Zillow home price data, we looked at the scatter plot of price versus living area. It sure does look linear. And the price versus number of bedrooms. This also looks reasonably linear, except here there's an obvious violation of the equal variance assumption. The points are not spread out at all with one-bedroom homes, and they seem to get spread out more as you get more bedrooms. When we look at the residuals versus predicted plot, remember this is the one that we're supposed to put the horizontal line at 0 and look for evidence against the errors having mean 0. I don't see much evidence against that. It looks pretty balanced above and below the line. And we also need to look for the constant error variance on this plot. So here, it looks like if I move a couple points, I could make this thing look pretty good. So the obvious non-equal error variance we saw in the individual scatter plot for bedrooms versus price seems to have dissipated in the residuals versus predicted plot. So the tendency for homes with more bedrooms to have greater variability was accounted for in the model when living area was included. When we look at the QQ plot, it looks a little bit like it has an inverted S shape. So what I did, since we had so many residuals, over 1,000, I went ahead and plotted them in a histogram here on the right too. So you guys could get a feel for what these QQ plots correlate to in terms of a histogram, in terms of what the actual distribution of the residuals is. So we can see that these residuals do appear to be from a unimodal and symmetric distribution, but they just struggle a little bit in the tails. Remember, there are like 1,000 observations here and just a couple trailing off in those tails. So the large sample size with no outliers will make it so that confidence intervals and hypothesis tests on the mean will probably be okay. So now we get to talk about a different test that we're going to look at with multiple linear regression. In simple linear regression, we just looked at the tests on the individual coefficients, on the individual coefficient for the predictor. But here we're going to pay attention to something we call the overall F-test first. The overall F-test for regression tests the null hypothesis that all regression coefficients are 0 and the alternative that at least one is important. In our regression example, the null hypothesis that all regression coefficients are going to be 0 is that the beta for living area and the beta for bedrooms are 0, against the alternative that at least one of these does not equal 0. It's basically asking, are any of these predictors important to predicting home price? So we can carry out this test with our output from the screen. Notice that we have our F statistic and our p-value right here on the bottom of our output. So the F statistic is 732.2. and the p-value is teeny tiny. It's less than 2.2 times 10 to the negative 16th. So the conclusion is that there's overwhelming evidence for the alternative, that at least one of the predictors in this model is important. If the F-test rejects the null hypothesis, you want to be thinking about an ANOVA here where we tested whether there was anything going on with any of the means, and once we figured out that there was, then we looked for where. Similar here in multiple regression. If that F-test rejects the null hypothesis, then we're going to look at the tests for each predictor. And again, we're going to let R compute the t statistics and the p-values for us. If we fail to reject the null hypothesis for a coefficient, it doesn't necessarily mean the predictor's not important. Remember, it only means the predictor's not important to the model after accounting for the other predictors. So the coefficient beta j can be different from 0 even when there's no simple linear relationship between y and xj. And it's even possible that the multiple regression slope changes sign when a new variable enters the regression. the same way we saw what happened when we had living area and bedrooms. Bedrooms went negative. So let's practice drawing conclusions for the hypothesis tests for both coefficients in this regression. Let's start with living area. So we've got our output for living area up here. The t-value is 30.18, and the p-value is less than 2 times 10 to the negative 16th power again. So what should we conclude? There's overwhelming evidence to conclude mean sales price changes as living area increases after accounting for number of bedrooms. Notice that the alternative hypothesis is not equal to. If we want to do a direction, we need to make sure that the slope went in the direction that we thought it was going to, and then cut that p-value in half. So these p-values are for non-directional alternative hypotheses. All right, let's try for bedrooms. So again, we've got our output for bedrooms. The test statistic is negative 2.69, and the p-value is 0.007, still tiny. So again, we're going to have overwhelming evidence that mean sales price changes as number of bedrooms increases after accounting for living area. So again, we're not looking at the sign of the estimate. These p-values are for the not equal to alternative hypothesis. If we want to do a directional hypothesis, we need to make sure that sign went the way we thought it was supposed to, and then cut the p-value in half. Okay, so we can do confidence intervals also. So I've used our conf_int of fit function in R, and we want to interpret the interval for living area. So if we look at the interval that we got out for living area, it's right here. So remember that this is on the slope for the coefficient for living area, right? And what is the beta coefficient? That is the change in the y over the change in the x by 1 unit. So what's our y here? Home sales, home price. And our x for this particular one is living area. So we're going to interpret it as living area increases by 1 square foot. Both of these are positive, so that means mean home price increases by between $87.74 and $99.94. And remember, we have to add the caveat after holding number of bedrooms constant, or after accounting for the number of bedrooms a home has. So with 95% confidence, we expect sales price to increase by $87.74 to $99.94 for each additional square foot of living area after accounting for the number of bedrooms. And now let's interpret the confidence interval for living area based on increasing the square footage by 1,000 square feet at a time instead of by 1 square foot. Often when people talk about the size of a home, they refer to it in thousands of square feet. It's a 2,000 square foot home. It's a 2,500 square foot home. It's a 3,000 square foot home. So we usually don't talk about it in increments of 1 square foot. So I wanted to show you how you could do this. It's going to be the same interpretation, except instead of if we increase square footage by 1, we increase living area by 87.74. If we increase the square footage by 1,000, we just multiply that increase in the home price by 1,000. So it's the same interpretation we had previously. With 95% confidence, after accounting for the number of bedrooms a home has, we expect sales price to increase by between $87,740 and $99,940 for each additional 1,000 square feet of living area.